this topic is basically equilibria. According to your syllabus breakup, it includes topic 10, 11, and 12. And we shall try to cover topic 10 and 11 the maximum in this chapter, that is equilibria. Okay.
Okay.
Now, first of all, we have a revision so that you can bridge up the AS topic 2. First is the term we come across commonly. It is reversible reaction. You can look this. Reversible reaction. Reversible reactions. Reactions which proceed in both directions. That is forward and backward. Reactants and products are shown in the chemical equation, and you put reversible sign. You put reversible sign for the such reaction. So this is we went through. We gone through in AS dynamic equilibrium. Dynamic equilibrium, a stage of a chemical reaction. A stage of a chemical reaction when rate of forward and backward reaction is maintained. A dynamic equilibrium means a reaction in which rate of forward and backward reaction is maintaining. Furthermore, the concentration of reactant and product is maintained to. This is it is better, no need to show equally, means maintain to. What is meant by this? Can you explain this statement?
So in a closed system, a reversible reaction will reach dynamic equilibrium when the concentration of all the reactants is equal to all the products, and the rate of the reaction is the same as well.
This is same as well. It is like this. If I quote an example, like this is N2 plus H2, let's say. This is reversible sign, NH3. This is, you put 2, this is 6, and this is 3. Rate of change, what is meant by rate of change means, for example, initially you put into a system certain moles of N2, certain moles of H2, certain amounts you have added. It means initially, if you look this, initially this is 100%. And initially there was no product, that's why it is 0. With the passage of time, N2H2 is utilized, and it is going to deplete, decreasing, and product concentration would increase. And after, if there's a closed system, it means a certain amount of NH3 is formed, and above that amount is not possible. It means that is the saturation point of NH3. Maximum it is formed. Like if I say to make you clear, if it is 20% form, if it is 20% form from the reactants which were available, it means there would be 80% reactant remain. Out of 100, 20% are being used up and shifted to form product. And if we say this, if to make you clear that 20 and 80, the figure for understanding purpose, this figure may be any one, means it shows the concentration exposed for understanding purpose. If there occurs a dynamic equilibrium, then this 20 and 80 figure is maintained. Means the amount from amount of NH3 shifted backward side, and it will be compensated when your reactant will react together to produce certain amounts, which gives the figure 20. And it means 80 and 20 figure is maintained. So basically, it is rate of change is maintained. Mean backward side, rate is maintained, and forward side, rate is maintained. Means when the rate is maintained, the figures which you are getting at dynamic equilibrium of the product side and reactant side, this is also maintained. So this is what we say rate of change from reactant to product and product to reactant is maintained. Dear sir, is it clear?
Yeah.
Basically, this is next is there is a principle, and it is called Le Chatelier principle. Can you tell what is meant by this?
In a closed system, when you change one of the conditions, so for example, temperature, pressure, or concentration, the reaction will counteract that change to bring it back to equilibrium.
Yes, good. For example, this is a system consisting of N2, H2, and H3. For example, if your purpose is to produce NH3 in your plant, in your industry, it means 80% your reactant remain unchanged. You can't throw it. You can't remove this because it will cause great loss. What would happen? You will break the dynamic equilibrium. You will break the dynamic equilibrium. You remove certain amount of NH3, like it means 20% is shifted. If you remove 20% up to maximum level, it means your position of dynamic equilibrium will be disturbed then. It means at dynamic equilibrium, there would be a ratio maintained of product and reactant, and that ratio would be affected. If you remove NH3, it means it will stop moving backward and start going towards the forward side till a new position is maintained. For example, if the ratio was 20/80, this is a dynamic equilibrium. When you get, it means it is 1/4. It is 1/4. The answer is 1/4. It means the answer is 0.25. It is 0.25. Is it so?
Yeah.
When you remove this, it means it will be affected Again, this 20 and 80 figure will be changed. When you remove 20, it means your 0.25 ratio would be affected. It means 20 figure now is decreased. Then again, in order to achieve this ratio of 0.25, it means it start going up forward side. This 20 and 80 will be changed, but the answer would be again 0.25. When there will be 2.25 ratio of product and reactant, it means again the position of dynamic equilibrium is achieved. So it means ratio is maintained like 1/4, but concentration of reactants and product at dynamic equilibrium, it would keep on changing. It would keep on changing. Like over here, 80-20, in another, the ratio would be some other, there will be some other figures, but again, the ratio 0.25 would be same. So this is Lee Chatelier principle. Dear sir, can you read this? It is readable easily.
Yeah.
If you read this, can you read Lee Chatelier principle?
Le Chatelier's principle, scientist who discovered the laws of equilibrium. The principle states if some changes is made on a system at dynamic equilibrium, the reaction goes towards the side which nullifies that change in order to get a new position of dynamic equilibrium.
Is it clear?
Yeah.
So this is basically, this is a scientist who discussed this all factors, how they are going to affect. Next is, now it is the same example I have given you, like there are reactants A plus B reversible C plus D. This is reversible and it is under dynamic equilibrium. A plus B is 100%, C plus D is 0%. A plus B is decreasing, C plus D increasing. And like 80-20 reactants left over 80, products form 20. So this is the same, it means the ratio product and reactants maintained, and what we have discussed right now. And in this, in order to make more clear, for example, at dynamic equilibrium, your reactants left over are 40. So 40 means it is a figure showing reactant left over at dynamic equilibrium and product form 20. And if you get the ratio, it is 1/2, product over reactant. And it means if you remove certain amount of product, it means the reaction stop moving backward side and goes on forward. And again, the new concentration is achieved like 10 and 20. 20 is decreased to 10, 40 is decreased to 20. Concentration, that is called position of equilibrium, is changed, but ratio is 1/2. Ratio is 1/2. Again, you remove more product. This 10/20, it would be affected. Then the new position is achieved, that 5/10. Again, 1/2 is maintained. It shows if you change the concentration of component at dynamic equilibrium, the ratio is maintained, but the new position of dynamic equilibrium is achieved. And this is the summary of this whole discussion. Next is factors we discussed in AS2. In AS, we also discussed this concentration. If you want to favor forward side, there are two ways. Asad, can you recall what are the two ways if you want?
Increase the concentration of the reactants or decrease the one of the products.
One of the products, you can say, it means you can stimulate, you can move the reaction forward side. This is. What about pressure?
The reaction, if you increase pressure, it will favor the side with less moles of gas, and if you decrease the pressure, it will favor the side with more moles of gas.
Good, good. For example, if I give you this example, let's say you have a closed system. This is your closed system, and in this you have HI, H2, I2, all are gases, and there is a dynamic equilibrium is H2 plus I2, this is, and these are all gases. These are all gases. Can you notice the change by increase or decrease in pressure on this system?
If you increase pressure, it will favor the left-hand side. If you decrease pressure, it will favor the right-hand side.
You're not looking. I didn't balance this equation. Can you look?
Oh,
Can you look?
2 HI.
2HI. If I put 2, then would
Then
be
pressure will have no impact.
this is the point. You have to look into and see the number of moles on both sides are equal. If they are equal, then there would be no effect on forward and backward side. This is. Next, about the temperature. Can you recall the effect of temperature?
If you increase temperature, it will favor the endothermic reaction. If you decrease temperature, it will favor the exo.
Good. And how can you decide this is endo and that is exo?
If the enthalpy change is negative, then it's exo. If it's positive, then it's endo.
Good, good. This is very good point. Exactly. Next is
This is the next one, catalyst.
no. This is basically three factors which affect dynamic equilibrium. Basically, factors.
All right.
Okay. So now, next is equilibrium constant. That is AC. And in AS, we also discussed this. Is it so?
Yeah.
K, this is C. C. Can you recall what is KC?
Like it's the I don't know how to describe it.
Yes.
The like simplest ratio of molecules needed to maintain dynamic equilibrium.
Actually, all right. I'm repeating. I'm going to recap. Okay. I'm going to recap.
Okay.
Actually, basically, this is KC. K means constant, equilibrium constant. C means concentration. Equilibrium constant in terms of concentration. In terms of concentration. For example, you can look, there's a container. You can look, this is a container, and in this container, you can look, the volume is 1 dm cube, and you have added N2H2 initially, and there was no NH3. With the passage of time, N2H2 are being used up, and their concentration would decrease because the volume is 1 dm cube, and the moles available in this of N2H2, this is their concentration. And when a dynamic equilibrium is achieved, then NH3, you get NH3 up to maximum level, that is a saturation point. It may be any concentration. It means Kc is Kc refers to, it is a ratio, it is the ratio of product concentration, products concentration raised to their respective molar concentration, and reactants concentration raised to their respective molar concentration. Yeah, or you can simply, you can say they products form the concentration of product at dynamic equilibrium, and concentration of reactants at dynamic equilibrium, and it is the ratio of both. So basically, this is the ratio. If you look this, like this is the equation, and this Kc expression, we use the term Kc expression. Kc expression, you can look Kc expression, Kc, this is NH3, and square bracket shows the concentration. This is the way to show concentration. So concentration is square bracket and raised to power 2, and N2H2, and its moles are 3, and that's why H2 raised to power 3. So this is 3 basically. 3. So what this is basically the ratio of product and reactants concentration at dynamic equilibrium. And if you want to derive the units, so this is mole per dm cube, mole dm minus 3 square, and this is cube H2, this is cube, the mole per dm cube raised to power 3. So basically, this will be cancelled out, this 3 mole square dm minus 3 minus 6, it comes. It will be minus 6. So basically, it will be minus 6, and mole minus 2 dm 6. If you shift mole dm minus 6 above, so this is the unit. So basically, Kc refers to the ratio of concentration of product and concentration of reactants at dynamic equilibrium. So this is, and there is an example over here. For example, you have N2H2 reversible NH3. This is the equation. You have closed system. N2 initially were 3 mole in a container. We suppose the container is 1 dm cube, and H2 5 mole. And at dynamic equilibrium, NH3 formed 0.5 mole. It is provided in the question. 0.5 mole. The container is 1 dm cube. That's why it becomes concentration. 0.5 mole per dm cube. And now you compare N2H2, NH3. One, to produce 2 mole NH3, you have to make react 1 mole of N2, 1 mole of N2, and you have produced 0.5. How much N2 required? This is X. If you cross multiply, you get 0.25. Likewise, of H2 and H3, to produce 2 mole, you need 3 mole H2. If 0.5 mole is X, cross multiply, you get you calculate this figure, 0.15 or 75. You can check this. So basically, these are the mole per dm cube. And now you put the value in Kc expression. This is Kc expression basically. This is Kc basically 0.5 raised power 2, and H2 is 4.25 because used up are 0.25, and H2 is 4.25 and N2 is 2.75. So this is the concentration of reactants and products at dynamic equilibrium. Now you put the value, and get the answer, and this is the answer. Now please have a look. Is there any confusion?
No.
Okay. Next is next constant. Equilibrium constant in terms of pressure. That is Kp. Primarily, we have discussed Kc. Now it is Kp. That is equilibrium constant in terms of pressure. This is same thing. Now, if I say, yes, look carefully. If I say concentration is directly proportional to pressure, is it right statement?
Yeah. Or is it inversely proportional, not directly?
Can you prove mathematically inversely or directly? Can you prove experimentally on the page I have shown?
Um. Oh. So if I do.
It is about 1 minute left, and you should rejoin. Is it okay?
Okay.
No, no. This I I was saying, you you give mathematical proof, uh,
Oh,
relationship of concentration and pressure. Relationship of concentration and pressure. Directly or indirectly, what is it?